Hello students, welcome back. We just went through three very important theorems. Two of them really super important. One, in terms of importance, yes, but the proof was so hard, so complicated that I don't think anybody can reproduce those. Of course, I'm talking about this one. If you have m generating vectors and n linearly independent vectors, then the number of generating vectors is always greater than or equal to linearly independent vectors. Hard to prove, but remember the result. Now these two. The minimal set of generators is basis. Maximal set of linear independence, also that's basis. These two, I have written these in the exam many times. As a matter of fact, even though I did those in classes and I picked those up in exams and wrote them anyway again, sometimes both of them. So these are super important. Let's see, how do they work? Generators, so number of generators can be generally more than number of linearly independent elements. So throw away, and go down, down, down until you reach a point you cannot throw anything away anymore without sacrificing the generating. You just reached the minimal set of generators, and that's the basis. How about the other way around? Number of linearly independent vectors is always less than or equal to number of generating vectors. So if you start with small number of linearly independent vectors, maybe you can add more, and at some point you're going to reach a point that you cannot add any more without sacrificing linear independence. You just reached maximal set of linear independence, and that's a basis. That theorem? Difficult, yes, but not impossible, and these two, I've written those as exam problems multiple times, so please study. I may do it again, maybe or maybe not, but anyway, in the past I have. Let's consider some other applications. Also, implications are important too. Alright, let V be an n-dimensional vector space, which means it has a basis W1, W2, all the way to Wn. Alright? Alright. Let V1, V2, V3 all the way to Vn be linearly independent subset of V. Then it's a basis. So in order to have a basis, what? We have to have generating and also linear independence, right? Generating and linear independence. Linear independence is already given here. Is it also generating? Well, that's something we'll have to establish. How do you do that? Well, we're going to be using this one. Maximal set of linear independence. So we're going to argue that this is the maximal set of linear independence. Therefore, it's a basis. All right? If I add one more, then it's not linear independent anymore. How do I do that? All right. Add one more, n plus 1. And then, okay, if this is linear independent, you will be in this kind of situation. Let me see. Let me get this statement down here. Okay, let me copy and paste this thing down here. Okay, let's go back. V1, V2 all the way to Vn. I want this to be the maximal set of linear independence. Okay, we put proper subset, add one more vector, and assume this is linear independent. But then again, dimension of V is n, therefore there is a basis, W1, W2, W3 all the way to Wn. And how do we draw contradiction? This W's generate V. And number of generators is n, and number of linearly independent vectors, it's n plus 1. Wait a minute, do we have n greater than or equal to n plus 1? according to this theorem, that's what we should have. You see, number of generating vectors is always greater than or equal to number of linearly independent vectors. Now, these are bases, so number of generating vectors, n, is greater than or equal to number of linearly independent vectors, n plus 1. But that doesn't make any sense. N cannot be greater than or equal to n plus 1. There goes the contradiction we wanted. So conclusion, this is a maximal set of linear independence, and therefore it is a basis. Okay, how about the next one? Subspace and dimension. How about this? Let W be a subspace of a vector space V, and if the dimensions are the same, then V is equal to W. Dimensions are the same, that means this is n-dimensional, that too is n-dimensional. We are talking about comparing just n vectors. They are finite for many vectors. How about V equals to W? There are infinitely vectors in V and also infinitely many vectors in W. So this is far more complicated, and this is much simpler, yet this simple condition is generating this much more complicated condition. Oh, okay, all right. That's worthy of something. So let's prove it. Okay, all right. This is just expression of the same thing in formal form. W is a subset of V, and dimension of V and dimension of W are the same, then V and W are the same. Okay. What kind of strategy am I going to use? We're going to select arbitrary element of capital V, and we're going to show that that element belongs to capital W by proving that V, the vector V, is a linear combination of basis elements of capital W. Okay, all right, let's begin. We already know NW is a subset of V, so let's prove the other way around. So let's begin with basis W1, W2, W3 all the way to Wn, which is a basis of capital W, but then again, it must be a basis of V as well because of the dimension, you see? Yeah. If you replace all those in theorem 2.3, if you replace all those V1, V2 all the way to Vn by W1, W2 all the way to Wn, then we have the conclusion here. These are linearly independent. Linearly independent. So it's a basis of V. You see? What are two properties of basis? Generating and linear independence. Here we are using linear independence. W1, W2 all the way to Wn are linearly independent. And same dimension and linear independence, so it's a basis. So it's a basis of V, not just basis of W, which we started off with, basis of V as well. So for arbitrary element of capital V, it can be written as a linear combination of element of W, so it's in capital W. So there goes the proof. How about the next one here? Let capital V be an n-dimensional vector space and R be a positive integer less than n. Okay, all right, less than n. Suppose further that V1, V2, V3 all the way to Vr are linearly independent. Then we can find, next vector R plus 1, Vr plus 2, Vr plus 3 all the way to Vn, such that this is a basis of capital V. Okay, all right. So first R linearly independent, and then we just add more linearly independent, more linear independent, more linear independent, until we reach the maximal set of linear dependence. So it's going to be basis of V. That's going to be the strategy. Okay, let's prove it. All right. V1 to Vr cannot be a basis of V. You see, basis is, number of basis vector is unique. We proved it, right? It's linear independent, so it is not generating, and it must not be maximal set of linear independence. See, number of basis factor is unique. We proved those in the previous section. So strictly less than R. So this is not the maximal set of linear independence. So there got to be something more, and then make a superset. And then one more, make a superset, because the previous was not the maximal. We can add more. Now, is this R plus 1 equal to N? In that case, we are true, but still not yet. Then by the same process. This is still not maximal, add one more. Still not maximal, add one more. Until you reach the dimension. Just repeat. So if you can call it a proof, I don't know whether this can be called a proof as a matter of fact. It's just too heuristical. But yes, that can be called a proof, yes. But I don't know whether memorizing all these or remembering all this idea is really worth it, though. Final topic here. All right. Let capital V be an n-dimensional vector space and W be a non-trivial subspace. Okay, all right. So non-trivial means there is a non-zero vector in there. Okay. Then W is also has a basis, and dimension of W is less than dimension of V. I see. This is gonna be hard part. Also has a basis. You see, existence of basis. If basis exists, then the number of basis factor is a dimension. That's what we have been doing. Does a basis always exist? Well, that's sometimes a problem, and that's something we have to do. So this is likely to be a little bit tricky, but the proof is going to be kind of constructional, kind of like this, adding one more if necessary, adding one more if necessary, kind of thing. Let's begin. Okay, if W is a trivial space, then there's nothing to do. Dimension is just 0, nothing to do. Okay. And then dimension of 0 is less than or equal to dimension of V. So, well, everything works out okay. If W is non-trivial, which means there is a non-zero vector, let's say W1, then let's see if W1 generates the entire W, which means W has dimension 1. In that case, dimension 1 is less than or equal to dimension of V. That's certainly true because this one is, again, non-trivial, greater than or equal to 1. Certainly fine. Now, if W1 does not generate entire capital W, then it's not a basis. So it's not a maximal set of linear independence. So you can add more, W2, and then check. And then you see, and W and W2. So if this generate entire W, then this is two-dimensional. And then W1 and W2, those are linearly independent family within capital V. So this one is greater than or equal to 2. So still it works out. And then repeat. It'll have to stop somewhere. So what do you get? W1, W2, W3, and it'll have to stop somewhere at WR. So basis exist, hard part done. And as for this dimension less than the dimension of capital V, that's actually easy because this is linear independence. And then this dimension is number of maximal set of linear independence in capital V. And this one is just linear independence, not necessarily maximal at V. Maximal at W, yes, not necessarily maximal at V. So you may be able to add more, or maybe you got completion, so we have equality. Either way, it works out. So that's the kind of proof, if you want to call it a proof. But still, maybe it's worthwhile to remember the result. That's about it.